So, in the last lecture we were looking at the use of similarity transforms, first for transport into infinite medium. We had first considered the solution for the transport into a semi-infinite medium that is bounded by a surface which is at a different temperature, and we looked at the evolution of that with respect to time. And the second, the injection of a pulse into an infinite medium of a finite mass within an infinitesimal thickness and its evolution in time. Okay. And the third case we were considering the last time was the diffusion into a medium of finite thickness. Okay. That is where we have a moving interface. The interface thickness evolves with time. Okay. So, that was the third case that we were considering. Specifically, we were considering the expansion of a melt pool above a solid. Initially, the solid and the solid is at a temperature equal to the melting temperature Tm, and at time t is equal to T naught, I impose a temperature at a higher a surface at a higher temperature, okay, such that the temperature T naught here is actually higher than Tm. Okay. And since T naught is higher than Tm, I have a temperature profile which decreases within the material. Okay. I have a temperature profile that decreases within the material. Okay. And because of this, there is heat that is transferred to the interface, and that heat transfer to the interface melts the material at the interface, and the thickness of the molten layer expands in time. Okay. So, we have an evolution of the temperature profile in a material whose characteristic length scale is increasing with time, and we were trying to find out what is the rate of increase. Okay. So, that was the problem. Temperature scaled the usual way such that it is 1 at z is equal to 0 and 0 at z is equal to 1. The coordinate scaled by the height, which is a function of time. Okay. The coordinate is scaled by the height, which is a function of time, and therefore, if I impose these scalings in the conservation equation and use chain rule for differentiation, okay, for expressing the time and the spatial derivatives, I get an equation, a similarity equation, in which, okay, on the left side I have h by alpha times dh by dt, okay, as the parameter. Note that h is a function of time, and but however, I can get a similarity solution only if this combination h by alpha dh by dt is independent of time. Okay. That is the necessary condition for a similarity transform. If it depends on time, then the equation is a function of z star and time. It is not a function of z star alone, okay, and therefore, I cannot solve this equation. Okay. So, therefore, I have the equation is, okay, minus p by z star dt by dz is equal to d square t by dz square, where p is given by this expression. This is also equal to h by alpha dh by dt. Okay. Okay, with the Jakob number J A, okay, where J A is given by this one. So, this is the equation, boundary conditions and the condition for the parameter p, which has to be determined self consistently after evaluating the solution and getting the derivative at z star is equal to 1. Okay. So, that is the equation and the solution. Okay. And we were examining last time how to solve this equation. Okay. In the last class we were examining how to solve this equation. When we had discussed heat conduction into an infinite medium, if you recall, I told you that the solution is in the form of the error function. Okay. the error function is a solution of the equation minus 2 z df by dz is equal to d square f by dz square. Okay. That is the equation. The solution, there are two solutions for this. It is a second order differential equation. There are two solutions. One of them is obviously a constant, because if you just substitute a constant, both the left and the right sides are 0. The second solution is of the form is equal to the error function of z, okay, is equal to 2 by root pi integral 0 to z, okay, dz prime e power minus z prime square. Okay. Okay, that is the error function solution. That is the second solution, okay, to the equation. And the derivative, okay, df by dz at z star is equal to 0 is equal to just 2 by root pi. Okay, that was the function that we had. Okay. Now, in this case we have minus p times this, the coefficient. Okay. And if you recall, I had also told you that when you have a different coefficient there, you can get a solution in terms of the error function, except that now if you have an equation of the form of this form, the solution is going to be t star is equal to error function of z root of p by 2. Okay. When we had done that discussion earlier, the coefficient I had used was a, if you recall, z root of a by 2, okay, times a constant plus a second constant, okay, because I told you that one solution is the error function, the second solution is a constant. Okay. And in order to determine these constants, I have to use these conditions: t is equal to 0 at z is equal to 1 and t is equal to 1 at z is equal to 0. Okay. If I substitute these two conditions, I will get, okay, I will not go into the details. What satisfies the boundary conditions is t star is equal to 1 minus error function of z star root of p by 2 by error function of root of p by 2. Okay. That is the final solution. Okay. At z is equal to 0, okay, the error function is 0 because it is an integral between 0 and 0. Okay. This integral for the error function at z is equal to 0, it has to be 0. Okay. If you recall, I had drawn the error function for you versus z star. When we discuss the error function, it starts from 0 and then it goes to 1, okay, far away. Okay. It goes to 1 in the limit as z goes to infinity, and it is 0 at 0. So, error function is 0 at 0, and therefore, it satisfies this condition t star, I am sorry, it satisfies this condition t star is equal to 1 at 0, and at z star is equal to 1, right, you can easily verify that this condition is satisfied. T star is equal to 0, okay, at z star is equal to 1, t star is equal to 0. So, the constant C1 and C2 are fixed by these two conditions, and this is the final solution I get for the temperature T star. Okay. We are not finished yet. Okay. I know that the condition that has to be satisfied is that dt star by dz star at z star is equal to 1. Okay. Okay. That has to be related to the parameter p. Okay. That has to be related to the parameter p over here through this condition. Okay. At z star is equal to 1, the Jakob number times this derivative with a negative sign has to be equal to p. Okay. So, let us evaluate what is the derivative at z star is equal to 1. Okay. The derivative of the error function is just okay. When I take the derivative of the error function, I will get 2 by root pi e power minus z star square p by 2 okay, into I will get a factor of root p by 2. Okay, so, let me just illustrate that here using this. Okay. Is equal to 2 by root pi, okay, e power minus z star square. Okay. That comes about just by taking the derivative of this one. Okay. If I take the derivative of an integral, I get the value of the integrand. Okay. So, I get 2 by root pi minus times e power minus z star square. Okay. When I take d by dz star of error function of z star root p by 2 and I use chain rule for differentiation, I will just get a factor of root of p by 2 here, 2 by root pi I will get a factor of root pi there. Okay. So, this comes out because I have taken a derivative by chain rule, and this coefficient, which is the derivative of the argument, okay, comes out as a derivative of the argument. Okay. So, that accounts for this factor square root of p by 2 here, okay, and I will get the final result as root of 2 p by pi e power minus z star square p by 2 at z star is equal to 1. And there is a negative sign here because there is a negative sign here. So, kindly note that I missed a negative sign. No, this is correct. Yeah. Yeah. Okay, this negative sign will give a negative sign here, negative sign here. And in both of these I have this term in the denominator here, I should not forget that. Okay. So, I will get here error function of that is a constant that is there in the denominator when you take the derivative. Okay. So, my final result is going to be equal to minus root of 2 p by pi e power minus p by 2 divided by error function of root p by 2. Okay. And now I have to put that into this condition, okay, that this condition here. P is equal to minus Jakob number into dt by dz at z is equal to 1 is equal to minus, okay, is equal to plus this is an implicit relation for p in terms of the Jakob number. Okay. So, given a value of Jakob number, I will find out what is the value of p which satisfies this relation, and that is the value of p that should be substituted into this equation. Okay. That is the value of p that should be substituted into this equation, so that the solution is self consistent. Okay. So, that the solution is self consistent. Okay. So, this is an implicit equation which has to be solved. And I can solve this, okay. This has to be solved numerically, okay. So, I can express the solution in the space Jakob number versus p, okay. You can easily verify when Jakob number is 0, p is equal to 0, okay. Okay, when Jakob number is 0, p is equal to 0, okay. And it increases for small values, okay, you have an expression, okay, for small values you have the expression that okay, p is equal to j a minus j a square by 3. Okay, that is the solution of this equation for small values of j a. Okay. And for large values, okay, for large values this becomes an implicit relation of the form j a is equal to root of p pi by 2 e power p by 2. Okay. So, it is j is actually increasing exponentially with p, okay, the limit of high, okay, Jakob number. Okay. So, and in between you have numerical values, okay, those numerical values you can use in order to find out what is the value of p given a value of j, okay, which satisfies this equation. Okay. And once I have a value, then I can use the second part of this relation. Okay. Once I have a value, I can use the second part of this relation. Okay. I know that p is equal to h by alpha dh by dt, okay, which is equal to 1 by 2 alpha dh square by dt. Okay. So, if my initial condition is that at t is equal to 0, h is equal to 0, the entire block was solid. Okay. So, the height of the molten layer was 0 at time t is equal to 0, because the entire block was solid. Then I know that h square is equal to 2 alpha p times t. Okay. So, h square increases proportional to t. Okay. As time progresses, h square increases proportional to t, or h increases proportional to square root of t. Okay. And the value of p I get from this dependence of p on the Jakob number. So, if I know what is the value, okay, j a is equal to c p into t naught minus t m by lambda. If I know what is this parameter, I can go to this graph and find out what is the value of p. Okay. Substitute that value of p in here to find out how h increases with time, okay, for this particular case, to find out how h increases with time. And the solution for this equation is just t star. Okay. The solution for this equation is this t star. Okay. The solution for this equation is this temperature as a function of z. Okay. So, but you do not really need to find out the solution. If you want to find out how h is increasing, I just need to find out what is this value of p here. That p comes from the dependence of the parameter p. P is effectively a Peclet number. Okay. It is a Peclet number based upon the height, and so it is effectively like h square by alpha t. Okay. It is like a Peclet number, okay, based upon the velocity of the interface and the thermal diffusivity. Okay. So, if I know what is this p, then I can calculate how the interface height changes with time. So, this is an example where I have used the similarity solution where in a finite domain, okay, in a domain where the thickness of the melting layer is increasing with time. If the thickness of the melting layer increases with time in a very specific way, okay, as given by this condition here. Okay. Okay. If the thickness of the melting layer increases with time in a specific way, which is given by this condition here, okay, and the temperature is a constant, okay, then I find that h dh by dt does in fact have to be a constant. Okay. And therefore, the left side here is a constant, and therefore, I can use a similarity transform. Okay. That is the basic idea here. Okay. If on the other hand the flux were a constant, I could not have used this, okay, because if the flux is a constant, then I do not get the condition that h times dh by dt is a constant. Okay. Because if the flux is a constant, then it implies that just dh by dt is a constant. That means that h is a function of time, and in the left side of this equation, this term is not a constant. Okay. So, for very specific cases where the compatibility condition on the variation of height with time results in an equation which does not depend explicitly on time, then I can use this similarity transform in order to find out the progress of the height with respect to time. Okay. In this particular case, since the temperature of that top surface T naught was a constant, as the height increased, the flux decreased as 1 over h, okay, as the height increased in the similarity transform. And in that case I could find a similarity solution, even though it was a diffusion in a thickness in a layer of finite thickness. So, let us look at an example of how we can use this. Okay, let us look at an example of how we can use this. Let us say that I have a molten ingot of aluminum of height 10 centimeters. Okay. Okay, let us say that I have a molten ingot of aluminum of height 10 centimeters, and I want to know, okay, the total height 10 centimeters. Okay. The melting temperature for aluminum is 662 . Rho is equal to 2700 kg per meter cubed. Okay. Cp is equal to 900 joules per kg per degree centigrade. The thermal conductivity K is equal to 220 watts per meter per degree centigrade, and the latent heat is 4 into 10 power 5 joules per kg. Okay. And I want to melt this entire 10 centimeters within a time period of 10 minutes. Okay. What is the temperature T naught that I have to apply, okay, at this top surface? Okay, what is the temperature that has to be applied at the top surface, so that this entire ingot of aluminum of height 10 centimeters gets fully melted within 10 minutes. Okay. So, that is the design objective, to find out what is the temperature that has to be maintained at the top, so that this entire melting takes place within a period of 10 minutes. Okay. So, that is the question. Okay. So, in order to answer that, right, so we know that h square is equal to 2 alpha p t. Okay. We have to find out what is alpha, the thermal diffusivity, the parameter p in this case. P, remember, depends on the Jakob number, and time t is equal to 10 minutes. Okay. What is the temperature difference that has to be maintained, so that this entire melting takes place? Okay. So, first things, alpha is equal to K by rho Cp, okay, which is equal to K is here 220 watts per meter per degree centigrade by rho is 2700 kg per meter cubed into 900 joules per kg per degree centigrade. Okay. And this is you can calculate this is equal to 9.05 into 10 power minus 5 meter square per second. Okay. So, that is the thermal diffusivity. Jakob number is equal to Cp into T naught minus Tm by lambda. Okay. We do not yet know what the temperature is. Okay. We do not yet know what the temperature is. Okay. However, what we do know is that h square has to be equal to 2 alpha times p times t, okay, and h is 0.1 meters, okay, it is 10 centimeters. So, 0.1 meters the whole square is equal to 2 into alpha, which is 9.05 into 10 power minus 5, okay, meter square per second. Let me write it elsewhere. Into P into T, which is 10 minutes, okay, into T, which is 10 minutes, which is equal to 600 seconds. Okay. Okay. And you can solve this to find out what is P. P is equal to this is equal to 0.092. Okay. Note that this value is small compared to 1, okay. It is about 0.1 or so. Okay. Knowing this value of P, what I should do is to take this particular value of P and find out what is the value of Jakob number that corresponds to that. Okay. So, for this 0.092, I should find out what is the Jakob number that corresponds to that particular value of P. Okay. In this particular case, since P is small, I can use this expression for the limiting value for small Jakob number. Okay. I can use this expression in order to find out the Jakob number to a good approximation, because we know that P is small. Okay. Okay. And so, this has to be equal to J A minus J A square by 3 for P small. Okay. And from this I can find out that J A is equal to 0.095. Okay, just solving this. Okay. And this is equal to C P into T naught minus T m by lambda, okay, which using the material properties is 900 joules per kg per degree centigrade into T naught minus T m divided by lambda, which is 4 into 10 power 5 joules per kg. Yeah. And I can solve this to get T naught minus T m is equal to about 42.2 degrees centigrade. And we know that the melting temperature is equal to 662. Okay, we know that the melting temperature for aluminum is equal to 662. Okay. This implies that T naught is equal to 702.2 degrees centigrade. Okay. So, this is the temperature at which I have to maintain that heated surface in such a way that the entire aluminum gets melted down to an extent of 10 centimeters, gets melted within a period of 10 minutes. Okay. So, that is the solution. So, this is a concrete example of where I can use this similarity solution for a time dependent length scale to actually design a process. Okay. So, this is an example of that. Okay. So, what I have shown you is that for a particular case where we have a time dependent length scale, if that length scale varies in a specific way with time, okay, in this particular case h has to be proportional to square root of t, or h square is proportional to t. If it varies in that particular way, then I can get a similarity solution, okay, with an unknown temperature gradient at the surface, and that temperature gradient at the surface is determined from the condition. Okay, that temperature gradient is determined from the condition that the amount of heat that is transmitted to the surface within a time delta t is equal to the amount of material that is melted within that same time delta t. Using that condition, I can get a condition based upon this non-dimensional temperature gradient at the surface and this dimensionless number called the Jakob number, okay, which is basically the ratio of the sensible heat and the latent heat. The sensible heat for increasing temperature from Tm to T0 and the latent heat. And once I have that solution, I can find out how much time it is going to take for a material of a given height to melt in a specific time. And I have shown you an example of where that can be practically used for the increase in the size of the melt pool. This completes our discussion of similarity transforms, where a partial differential equation in time and in position was reduced to a ordinary differential equation using a similarity transform. In the next lecture, we will look at transport in a domain of finite height. Okay. In this case, you do have a length scale in the problem, and therefore, you cannot reduce it to a similarity problem. How do we solve those problems? We will continue that in the next lecture. I will see you then.